It's the 12th of August, 1985, over the mountains of central Japan. Captain Masami Takahama is flying a Boeing 747 with no working flight controls. He has been doing this for 11 minutes. He has 21 left. What brought this aircraft down was not the thing that broke that day. Here is how it unfolded. 44 minutes earlier, at 18:12, Japan Airlines Flight 123 lifts off from Haneda Airport in Tokyo. It is going to Itami Airport in Osaka. The flight takes 54 minutes. It is one of the busiest domestic routes in the world. The aircraft is a Boeing 747 SR-46, registration JA8119. The SR stands for short range. Boeing built this variant specifically for Japanese domestic service, reinforced to handle far more takeoff and landing cycles than an ordinary 747. It was delivered in 1974. It is 11 years old. There are 524 people on board, 509 passengers, 15 crew. This is Obon, the festival week when Japanese families travel home to honor their dead. The aircraft is almost full. In the cockpit, Captain Masami Takahama, 49 years old, 12,424 flight hours. First Officer Yutaka Sasaki, 39. Flight Engineer Hiroshi Fukuda, 46. The 747 does not fly on cables. There is no direct mechanical link between the pilot's control column and the surfaces on the wings and tail. The pilot moves the column, and high-pressure fluid moves the aircraft. This is a hydraulic aeroplane. So Boeing gave it 4 hydraulic systems, 4 independent systems, 4 separate pumps, 4 separate reservoirs, 4 separate networks of lines. Lose system 1, and 3 are left. The aircraft flies normally. Lose 2, and 2 are left. The aircraft flies normally. Lose 3, and 1 is left. And 1 is enough to land. To lose control of a 747, all 4 have to fail at the same moment. The odds of 4 independent hydraulic systems failing simultaneously through mechanical fault are close to 0. That is the entire reason the number is 4. But all 4 systems run through the tail. Not because anyone chose it, because that is where the flight controls are. 4 independent systems. One place they all pass through. To take down all 4, you don't need 4 failures. You need 1, in exactly the right place. Between the pressurized cabin and the unpressurized tail sits a wall. It is called the aft pressure bulkhead. It is 4.5 meters across. Its skin is 0.9 of a millimeter thick, thinner than a coin. 18 panels, 36 stiffeners. Every single flight, it holds back a pressure difference of 8.9 pounds per square inch. Every one of those 4 hydraulic systems worked exactly as designed on the 12th of August 1985. It made no difference at all. So what could possibly break all 4 at once? To answer that, you have to go back 7 years, to a landing that everybody survived. On the 2nd of June 1978, this same aircraft, JA8119, was flying as Japan Airlines Flight 115. It came in to land on runway 32L at Itami, Osaka. It came in nose high. The tail struck the runway. 25 people out of 394 were injured. Nobody died. The damage was to the aft pressure bulkhead. It was cracked. Boeing sent technicians to repair it. Boeing's own approved repair procedure called for 1 continuous splice plate, secured with 3 rows of rivets, so that the upper skin and the lower skin were each attached to the plate by 2 rows. That is not what was installed. The technicians used 2 separate splice plates instead of 1 continuous one. Over part of the joint, the plate only reached the bottom 2 rows. The upper skin was attached by a single row of rivets. Not 2, 1. A filler plate was fitted into the gap where the splice plate should have been. According to the final report of Japan's Aircraft Accident Investigation Commission, using 1 row of rivets where 2 were required reduced the strength of that joint by 70%. Nobody caught it. The Boeing inspector missed it. The defect was covered by a fillet seal, a bead of sealant laid over the joint. Japan Airlines' own post-repair inspection missed it too. The aircraft went back into service. And then it flew. Every flight, the cabin was pressurized on the way up and depressurized on the way down. 8.9 psi. cycling against a joint that had 30% of the strength it was supposed to have. The metal fatigued. A crack started. It was far too small to see. It flew like that 12,318 times. In December 1984, the aircraft went through its last major inspection. Investigators later estimated that the crack was around 10 millimeters long by then. The detection rate for a crack of that size, in that position, by visual inspection, is roughly 1 in 10. Nobody saw it. The aircraft was cleared to fly. For 7 years that joint held. It was not strong. It was just not yet weak enough. On the 12th of August, 1985, JA-8119 takes off for the 12,319th time since the repair. At 18:24, 12 minutes into the flight, the aircraft is approaching cruising altitude, around 24,000 feet, over Sagami Bay. The bulkhead fails. The skin tears open along the 1978 repair joint. The hole widens to several meters in a fraction of a second. Pressurized air from the cabin blasts backwards into the unpressurized tail. The pressure wave tears off more than half of the vertical stabilizer, the tall fin at the back of the aircraft, along with the rudder, the tail cone, and the auxiliary power unit. And all 4 hydraulic lines run through exactly that space. All 4 are severed in the same second. The fluid drains away. The elevators are gone. The ailerons are gone. The rudder is gone. The spoilers are gone. Everything Boeing built 4 systems to protect is now dead weight. On the cockpit voice recorder, there is a bang, then the cabin altitude warning horn. Takahama calls for the emergency transponder code, Squawk 770 Girid. Fukuda, the flight engineer, reads the panel. Hydraulic pressure down. Amber light on. Takahama calls Tokyo Control. Tokyo, JAL-123. Request for trouble. Request return to Haneda. They do not know the tail is gone. There is no camera on the back of a 747, and nothing on the flight deck tells them what they have lost. The crew believes a door has blown out. They are trying to save an aircraft, and they do not know how it is broken. They have one thing left. 4 throttle levers. So they fly with the engines. The engines hang below the wings, well under the aircraft's center of gravity. Push them forward, and the extra thrust pushes the nose up. Pull them back, and the nose drops. Push the 2 on the left harder than the 2 on the right, and the aircraft slews to the right. That is the entire control system now. There is no procedure for it. It is not in the manual, because the loss of all 4 hydraulic systems was not a scenario the manual was written for. The inputs are also slow. A control surface responds in a fraction of a second. An engine takes several seconds to spool up, and the aircraft takes several more to answer the new thrust. Every correction Takahama makes arrives late, and by the time it arrives, the aircraft is somewhere else. Without a tail, the aircraft begins to oscillate on its own. It enters a phugoid, a slow porpoising cycle, 90 seconds long, climbing and falling 3,000 to 5,000 feet each time. On top of that, a Dutch roll, a 12-second wobble, rocking 50 degrees right, then 50 degrees left. 3 men are hand-flying a 250-ton aircraft that will not stop moving, using controls that answer several seconds after they are asked. They keep it in the air for half an hour. Takahama flies. Sasaki works the throttles with him. Fukuda reads the panel and calls the altitude as it climbs and falls. On the recorder, the 3 of them are working the problem for 32 minutes. They do not stop. They are still trying to fly the aircraft on the last second of the tape. At 1840, they lower the landing gear. Not to land. Extending the gear adds drag below the center of gravity, and drag is one of the few things they can still add on purpose. It is an attempt to damp the oscillation. It works. For a while, the aircraft steadies. At 1847, Tokyo Control asks, "Can you control now?" Takahama answers, "Uncontrollable." The aircraft drifts northwest, into the mountains of Gunma Prefecture. The ground proximity warning begins to sound. Sink rate, pull up, pull up. The last words recorded from Captain Takahama are, "It's the end." At 18:56:22, Flight 123 strikes the side of Mount Takamagahara on the ridge known as Osutaka, above the village of Ueno in Gunma Prefecture. Elevation, 1,565 meters. The aircraft is banked 80 degrees to the right and descending at 18,000 feet per minute. 32 minutes have passed since the bulkhead failed. About 25 minutes after the impact, a United States Air Force C-130 finds the wreckage. It is still light. The crew reports a burning area roughly 300 meters across, with fires in about 10 places. They offer helicopter support. No rescue team reaches the mountain that night. The site is on a steep forested ridge, 63 kilometers from the nearest staging area, with no road to it. A helicopter passes over the wreckage after dark and reports no sign of survivors from the air. That report is accepted. 8,000 personnel are mobilized, and 880 vehicles, and 37 aircraft, and for the entire night not one of them is on the mountain. The first helicopter lands at 4:39 the following morning. The ground team sets out at 6:30 and reaches the wreckage sometime after 10, more than 12 hours after the crash. There are 4 survivors. All 4 were sitting in the last 7 rows. Yumi Ochiai, an off-duty Japan Airlines flight attendant, is trapped in the wreckage for 16 hours. Keiko Kawakami, 12 years old, is found in a tree. Hiroko Yoshizaki, 34, and her 8-year-old daughter Mikiko. Ochiai later testified about the night. She said she could hear other people around her in the dark, breathing hard, gasping. By morning, she could not hear them anymore. Doctors who examined the bodies said afterwards that some victims had injuries that would have been survivable if help had arrived sooner. Estimates of how many range from 20 to 50. The official post-mortem report stated that almost everyone died on impact. Those 2 accounts have never been reconciled. 520 people died, 4 lived. It remains the deadliest accident involving a single aircraft in the history of aviation. On the 19th of June, 1987, the Aircraft Accident Investigation Commission published its final report. The cause was an in-flight structural failure, caused by a faulty maintenance repair, leading to explosive decompression, loss of the vertical stabilizer, and loss of all hydraulic control. Boeing acknowledged that the 1978 repair had not been carried out according to its own approved procedure. Japan Airlines president, Yasumoto Takagi, resigned. A JAL maintenance manager, Hiro Tominaga, killed himself. So did Susumu Tajima, an engineer who had inspected the aircraft after the 1978 tail strike. Domestic air traffic in Japan fell by 25%. But the change that outlasted all of it was an engineering one. Flight 123. And, 4 years later, United Airlines Flight 232, which also lost every hydraulic system it had, forced the aviation industry to confront an assumption it had been building aircraft on for decades. Redundancy means nothing if the redundant systems share a single point of failure. 4 systems that all run through the same 3 meters of airframe are not 4 systems. They are one system, drawn 4 times. What the industry now calls common mode failure became a design problem in its own right. Hydraulic fuses, valves that seal off a ruptured line to preserve pressure in the rest, became standard fittings. Boeing built 4 independent systems so that no single failure could bring the aircraft down. In the end, 1 row of rivets brought down all 4. In 2006, Japan Airlines opened a building at Haneda Airport called the Safety Promotion Center. Inside is wreckage recovered from JA-8119. Among it is a section of the aft pressure bulkhead. Every new employee of the airline is required to go and look at it. And every year, on the 12th of August, the families climb Osutaka Ridge. The bulkhead section sits behind glass at Haneda. Every new employee has to stand in front of it. You can see the splice plate. You can see the joint. You can count the rows of rivets. There is one.